Cool. So this is the last week, and today what we're going to be talking about is finding transmission clusters. So far, everything that we've been doing has been very biology and kind of computer science focused, and we haven't done too much to actually connect it to the public health side. So today is now where we can bring all of that stuff that we've talked about and apply it to public health. Specifically, what we've talked about so far is given raw sequence data, how do I assemble a genome? How do I annotate the viral genome? In the middle of a pandemic, how do I sequence new viral genomes? And then given a bunch of viral genomes, we talked about how do I line them up nicely? We talked about, given that multiple sequence alignment, how do I infer an evolutionary tree? But today, now we're going to actually use those inferences that we've made to apply it to epidemiology. So the topic of today is finding transmission clusters. So here's an outline of today's seminar. Basically, I'm going to first define what are transmission clusters. Then I'm going to distinguish between what is called a molecular cluster versus a transmission cluster. And then we're going to talk about different techniques that people use to find molecular clusters. So first, what is a transmission cluster? So a transmission cluster is just a group of infected persons who are connected by transmission. So this could represent recent and ongoing transmission in a population. And what's important about transmission clustering is that if I can identify transmission clusters, it can help inform where I can target my prevention efforts. So one kind of overarching issue in public health is that we have limited resources, right? So ideally, in a perfect world, we would have unlimited money, unlimited human power, and we could do every single intervention to target every single person if possible. But the reality is we have limited funds, we have limited humans, right? We have limited kind of resources to be able to actually implement prevention efforts. So if I can identify transmission clusters, it might help me inform where I can best target my prevention efforts. So that's a transmission cluster. It's a group of infected persons who are connected by transmission. Either one person infected the other, or maybe they both had the same person infected both of them. Maybe it's kind of like a group of very recently infected individuals from the same source, but somehow they're grouped together in terms of their transmissions. Okay, so expanding that, a risk network is a group of persons who are infected or susceptible. So the transmission network is a subset of the risk network, right? So the transmission cluster is the folks who are connected by transmission. So it's only people who are already infected, versus the risk network is kind of a wider net. It's the people who are infected, so it's the transmission cluster, plus their neighbors who are at risk. So they're susceptible. They're not currently infected, but they are susceptible to becoming infected. So for example, with HIV, it could be like if someone is HIV positive and they have a non-HIV positive partner, that partner could be susceptible. So they would be in the risk network where they are connected to someone who is HIV positive, but they are not HIV positive themselves. So identifying transmission clusters can help us find the most susceptible uninfected persons. So going back to my HIV example, with HIV, there's what's called PrEP. It's pre-exposure prophylaxis. It's basically, some type of treatment that someone who is susceptible but not currently HIV positive can take to prevent them from getting infected with HIV. Or you could kind of target contraception, or if we're looking at injection drug users, you could do like needle exchange programs. But basically, if we can identify the transmission clusters, we can then reach out to those folks and identify, who are they in contact with? Who would be the most susceptible uninfected persons? Okay, any questions so far just about what are transmission clusters? What is the risk network? Feel free to unmute, feel free to raise your hand, feel free to type in chat. That make sense? Okay. So how do I actually identify transmission clusters? So one very popular way of doing this is through viral case surveillance data. So in general, if I notice that, if I'm tracking how many cases of a given virus are there in different geographical regions or in different populations, if I'm just keeping track of that count, I can see like, oh, there's an uptick in how many diagnoses there are in this specific area. So for COVID, we have those like case count per country or case count per county versus like any of these case counts. I can watch that data and see, is there a rapid increase in any location? However, one thing that I want to emphasize with regard to viral case surveillance data is that increases in cases might not actually be, like increases in the case count might not actually be because more people are getting infected than before. It could be because of increased testing. This was especially something that we saw with the COVID-19 pandemic. Early on in the pandemic, it was extremely hard to get your hands on tests. So once testing became more easily accessible, you expect the case count to go up just because more people that are infected are being able to get diagnosed. So that's just kind of one caveat to keep in mind, is that the case count is the number of infected people who were able to get tested and we kept track of. So it's actually a subsampling of the true number of cases. Okay, another possible way of identifying transmission clusters is through partner services and contact investigation or contact tracing. So basically what you can do is if you encounter newly diagnosed persons, you can survey or interview them to find people that they may have interacted with. And this happens with most diseases that I'm aware of, but especially with COVID-19 right now, contact tracing is really important. So this is common for HIV and sexually transmitted infections, but we're using it in COVID-19 as well. Basically just ask folks like, who have you interacted with, so that we can maybe reach out to them and get them tested as well. And the last one, which is going to be our focus, is molecular surveillance data. So basically, if we have some type of molecular biological data, for example, if we have sequence data, and this is what we are interested in this class. So with COVID, you might have seen like news reports that San Diego County is sequencing the wastewater to identify COVID-19, or to identify SARS-CoV-2 within the wastewater. And we have our massive testing where we're collecting samples, doing RT-PCR, all that good stuff. So this is kind of our personal interest in this class. Okay, so any questions about transmission clusters? Feel free to type in the chat, feel free to unmute. Yeah, basically groups of infected individuals who are connected by transmission. Okay, so the next section, I'm going to introduce a term called molecular clusters, and I'm going to distinguish it from this term transmission clusters that we just talked about. So a molecular cluster is a group of persons linked by molecular data. And for our purposes, molecular data is pretty much always going to be viral sequence data. So a molecular cluster is a subset of a transmission cluster. And the reason why it's a subset is that not every infected person gets their molecular data collected. So for example, with COVID-19 in San Diego, we don't sequence every single person who tests positive. We sequence a subset of them just because of limited resources, limited access to, to sequencing machines, limited access to the samples, all that good stuff. So, you have your risk network, which is everyone who's infected from a similar common source, as well as their neighbors who are susceptible. You have the transmission network, who is just the folks that are infected and connected by a recent source of transmission. And then you have the molecular cluster, who is individuals in the transmission cluster who have been sequenced, who we have molecular data about. And what's really, really important that I think if you read any papers related to molecular epidemiology, I think sometimes folks miss this, is that we really, really, really need to be conscious of missing data. We have to be conscious of people that are missing from our molecular cluster. So specifically, we have to be really conscious of the people that are diagnosed but not sequenced. So in other words, the people who are in my transmission cluster but not in my molecular cluster. And we also have to be aware of people that are not even diagnosed. So people in the risk network, but not in the transmission cluster. Okay, so any questions there? We have to be super conscious about missing data. when we make any inferences that we make. All right, any questions so far? Kind of makes sense? Okay. So how do I find these molecular clusters? In general, molecular clusters, it's kind of like a proxy for a transmission cluster, right? It could be missing people that we didn't get to sequence, but at least if we survey them, if we do contact tracing, something like that, we might be able to figure out information about the transmission cluster from the molecular cluster. So molecular clustering is a very kind of interesting epidemiological problem. And I'm going to talk about two different approaches for performing molecular clustering. One approach is directly using sequences that we collect from the patients. And the second approach that I'll talk about later is using the evolutionary history of the viruses, using the phylogenies. So first, how do we do molecular clustering directly from sequences? And to kind of motivate the approaches that are used, I'm going to go with an example scenario. So imagine that I have two people, person X and person Y. And imagine I collect a viral sequence from both of these people. So I have the viral sequence from person X, and I have the viral sequence from person Y. Let's consider a few scenarios. And in this notation, I just want to highlight d of x comma y is the distance, the pairwise distance between the viral sequences of the two. So when I use this notation, this is the pairwise sequence distance. So if it's 100%, that means that the two sequences are completely different. If it's 0%, that means that the two sequences are completely identical. But it's just the pairwise distance between the two sequences. Okay, so one scenario is, what if X and Y were infected from the exact same person? So if both of these individuals were infected by the same person, the pairwise distance between their viral sequences will be extremely small because there was just not very much time for the virus to mutate between those two transmission events. Okay. Does that kind of make sense? Okay. So another scenario is, what if person X and person Y were not infected from the same person, but they're in the same general group of infections? So maybe there was some common individual that infected someone, that infected someone, that infected person X. That same person infected someone, infected person Y. So they are both recently infected from the same general source. Maybe they're at the same concert, maybe it's the same kind of outbreak, but they weren't necessarily infected from the same exact person. So in this example, the pairwise distance between those viral sequences, it's not going to be as small as this first bullet because some time has passed between transmission events for a few mutations to accumulate, but the pairwise distance is going to be pretty small. So it's going to be small. It's the same recent source of infection, but it's not going to be as small as when it was the exact same person infected both of them. And then the last scenario that I want to go over is, what if X and Y were infected from completely unrelated sources? So let's imagine that it's COVID-19, and let's imagine I'm in San Diego, which has an international airport. Maybe one person recently traveled to another country, and one person, like maybe one person traveled to country A, one person traveled to country B. Both of them got infected in their respective countries that they visited. Then they came back. These two people happened to be in San Diego, and I happened to be able to collect viral sequences from both of them. But those viral sequences are going to be super, 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 super different because those sources of infection were completely unrelated. They're very far apart. Okay, so yeah, in that case, a lot of time has passed since the common ancestor of those two viral lineages. So a lot of mutations will have accumulated. The pairwise distance will be pretty large. Okay, does this make sense so far? Any questions? Okay, so the key takeaway is, the closer two individuals are with respect to transmissions, the smaller the pairwise distance between their viral sequences will be because there's been less time for mutations to accumulate. So this hopefully motivates a fairly intuitive approach for molecular clustering. If I have two people, X and Y, I can link these two people if their pairwise distance is very small. So what I could do is basically for every single pair of individuals, let's say that I've sequenced 100 people. What I could do is do every single possible pairwise comparison between their viral sequences. And if person X and person Y have viral sequences that have a small pairwise distance, let me link them. And then each of those resulting chains of links defines a molecular cluster. So I have an example to kind of show how this would work. Imagine that I have 4 people, and so I have person A, person B, person C, and person D, and I've drawn every single possible pairwise distance. So here, these are decimals that represent percentages. So maybe the pairwise distance between person A's virus and person B virus was 1% of the sequence was different. Maybe B to C is 1%. Maybe A to C is 2%. Maybe A to D is 5%. B to D is 5%. C to D is 5%. So I had all these viral sequences. I computed every single pairwise distance, and now I have drawn these potential links. I don't know if they're actually linked yet. I have to now define some threshold of small. So let's imagine that I say 0.01, so 1% difference is what I consider to be small. So if the pairwise distance is less than or equal to 0.01, I consider 2 individuals to be linked. So in this example, A and B become linked, B and C become linked, but none of the other pairwise distances are small enough to link those people. So one standard approach for doing molecular clustering is after I add these links, let me just output every single chain of connected nodes as a cluster. So in this example, A was not directly connected to C, but A was connected to B and B was connected to C. So I'm going to stick them all in the same group. And then D wasn't connected to anyone, so D goes in its own group. Any questions about what I just did? Feel free to unmute, feel free to type in the chat. Basically, compute all pairwise distances, define some threshold, any pairwise distances below the threshold, link those people, and then all of the chains that are connected are output as separate clusters. Okay, all good, nice. So like everything in this class, we fortunately don't have to do this ourselves. There's a tool called HIV Trace that does this for HIV, and it's also been used during COVID-19, where basically you give it a bunch of sequences, typically HIV, but it generalizes to other viruses, and it computes all pairwise sequence distances and outputs the molecular clusters. Okay, and one thing that's kind of important that I was a little bit hand-wavy about is I just arbitrarily told you 1% is our threshold in that previous example. So I just arbitrarily said, if the pairwise distances are less than or equal to 1%, link them. In reality, you don't necessarily know what that pairwise distance threshold should be. Is it 1%? Is it 1.5%? Is it 2%? So in practice, what people usually do is they try to motivate that pairwise distance threshold using survey data that they already know about pairs of individuals who have already told you that they're partners. So if you have information about like, oh, these people do indeed, like they know that they were infected from the same source, we can kind of come up with a pairwise distance threshold that links people together if we know in advance that they're linked, and hopefully doesn't link people together if we know in advance that they weren't linked from survey data or whatever other information that we have. Cool. So yeah, so finding that threshold, it's not trivial, but you can hopefully figure it out based on survey data or contact tracing. Okay, so that was how we find molecular clusters from sequences. And then the last thing that I want to talk about is how do we find molecular clusters from evolutionary trees? And let's just quickly recap how we can envision how evolutionary trees are related to the transmission network. So here we have the same transmission network that we've seen before. And remember, if I zoom in on a single transmission event, we can imagine that before the time of transmission, there's a bunch of viral lineages evolving within the host. Then at the time of transmission, one viral lineage goes from the host to the recipient, and this starts off its own evolutionary process within the recipient, and in the host, the virus continues to evolve as well. And then we collect a few viral lineages at random. This is like if the person comes in to get a nasal swab, if we're dealing with COVID-19, or with HIV, if we take a blood test. Somehow we've collected a random sampling of the viral lineages at the time that they came to get tested or collected or whatever. And then the evolutionary tree that we observe is the constrained tree only consisting of those specific viral lineages that we were able to physically collect. So this is what we observe. And remember, in the past few weeks, we've talked about, given sequence data, how can I infer an evolutionary tree from those sequences? So we hopefully have a way of reconstructing this directly from molecular data. So now how can I use that phylogeny that I've inferred to infer molecular clusters? Well, the viral phylogeny is heavily constrained by the transmission network. Specifically, if person X and person Y were infected by the same person, X and Y, if I have one sequence from X, one sequence from Y, those sequences are going to be very, very close together in the evolutionary tree. If X and Y were not infected from the same person, but they're in the same general group of infection, they're not going to be as close together in the evolutionary tree, but they'll still be pretty close. So maybe they'll be in the same kind of subtree. Versus if X and Y were infected from completely unrelated sources. So in my previous example, I said like maybe both of them went to different countries, got infected in those separate countries, and then came back to San Diego. So completely unrelated sources of infection. Then X and Y will be very far apart in that evolutionary tree. So similar in principle to how we were talking about the sequence relationships, where the closer together in the transmission network two people are, the closer their sequences were. Same thing here. The closer two people are in the transmission network, the closer they're going to be in the evolutionary tree. So similarly, I can think of ways of defining clusters using relationships from within the evolutionary tree. And there's quite a few ways to define clusters given an evolutionary tree. Maybe you define them as like all subtrees where the maximum pairwise distance is below some threshold. Maybe you define it as I cut the tree in some way. Maybe I cut super long branches and the resulting subtrees are clusters. There's a bunch of different ways that we could potentially define clusters in the tree. And just like with HIV trace, how we linked people based on pairwise distance, I could also take the same exact approach. I could link pairs of individuals based on pairwise distances, but instead of computing those pairwise distances from the tree, I can compute from the sequences, I can compute the pairwise distances directly from the tree. So a few years ago, I actually implemented a lot of these in a tool called Tree Cluster that you can check out. Maybe I'll go ahead and open it. But basically what Tree Cluster does is you give it an evolutionary tree that you've inferred from a bunch of viral sequences. You give it some threshold and you tell it what approach you want to use for clustering. So for example, you want the average pairwise distance in a given subtree to be below some threshold. You want the distance from the leaves to be some threshold. You want no branch lengths that are bigger than some threshold length. You want the maximum pairwise distance to be below some threshold. So it just has a bunch of different potential definitions for how you might define clusters, and then it just computes it for you.